Hello guys, so welcome back to our course. So in this lecture we're gonna continue our arithmetic designs. We explored subtractor, adder, subtractor and adder at the same time in the same circuit. We also did the multiplier. Okay, and another important design is a design that can compare the two numbers. So frequently we use compare two numbers, which is greater than which, or if they are equal. This is another, design called the comparator. Okay. And the smallest comparator that you can ever do is basically a comparator that can just, compare two numbers together. Just something like the half other, adding two bits together. Okay. So we have three cases. For example, if we compare these two bits and call them A and B, so you have the case that A is greater than B, A is less than B, and A is equal to B. So you can think of this binary comparator, which has two inputs. Each input is just one bit, as a box, and this box has two inputs: A, one bit, and B, another one bit. And then there are three outputs. E equal to B, E less than B, A is greater than B. Okay? This is really very simple design, because basically that can be converted to that truth table here. So you have here a truth table that describes the operation or the behavioral design, or the behavioral design of this comparator. So here you have the two inputs A and B. They have four combinations. Okay, and then you have A equal to B. This is the first output. Then A less than B. Then A greater than B. Okay, and look here. A equal to B is one in two cases. Basically, when A and B are zeros, and when A and B are one. Of course, these are the only two cases in which A equal to B. Other than that, A equal to B output is just zero. We also, if we look at the truth table, the four combinations, we noticed that only in one case A is greater than B, in that case here. And A is less than B is also in one case, this case. So this is the only case that A is less than B, really. And this is the only case in which A is greater than B. And that's why if we look at A less than B here, you will find that it's always zero, except in one case in which it's one, which is basically this case here. Okay? Again, the same for A greater than B. It's always zero, except again in one case, which is that case here, in which A is 1 and B is 0. So basically A is greater than B. Okay? Of course, if you do the Karnoff map, it will be very simple. Actually, you don't need to do the Karnoff map. It's really simple. You can just deduce, the equations just from the truth table. So let's do, for example, let's start by A greater than B. So A greater than B is only one in that case, in which A is 1 and B is 0. So this can be translated basically to A, B complement. If you want to do the Carnot maps, it's you can do it. It will be very simple like this. This is the two variable Carnot map. So A greater than B, 0, 0, 1, 0. So we have only 1, 1, which is that one here. So basically this is A, B bar. Remember, this is B bar. A, B bar. Okay? A less than B, again, you have only 1, 1 in the Carnot map. If you do the Carnot map, we'll just look at here. So the only case in which A is less than B is that case here, in which A is 0 and B is 1. So the equation should be B A bar or A bar B, whatever, the order. Now for A equal to B, you have two ones. So in 0, 0 and 1, 1. This is basically XNOR, because XNOR is the opposite of XOR. XOR, you count the number of ones in the inputs, all the inputs, and if the number of ones is odd, then the output will be 1. If the number of ones is even, the output will be 0. XNOR is opposite. If the number of ones is even, then it will be 1. If the number of ones is odd, then it will be 0. That's the case here. Look, A 0 B 0, the number of ones is 0, so this is considered even, so A equal to B will be 1. And A1 B1, last case here, the number of ones is 2, it's an even number, that's why A equal to B is 1 also. So basically this is XNOR. Or you can just write it in this way here. You have two ones in that place when A and B are 0, so this is A bar B bar, or 1 again when A and B are 1, so this is basically AB. So it will be very, very simple circuit in VHDL. Okay. One may say, okay, can I think in that design in another way? I mean, since it is basically 3 cases and I have 2 inputs, each one is 1 bit. Can I just make the output 2 bits? Then I will assign for each case, specific. I will assign for each case a specific case. I mean, something like this. So let's discuss this. So we have A, we have B. Then I will consider the output here. Let's call it state, something like this. Okay, I have here 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Then I will say the following. If the 2 inputs is 0, 0 or equal, basically, I will consider the output, some specific combination. So something like 0, 0. So whenever the output is 0, 0, okay, that means both inputs are equal. Then, so 0, 0 is basically to represent that A equal to B. Then I will say that whenever I have 0, 1, that means that A is less than B, which in that case here, so 0, 1. And whenever I have 1, 0, or 1, 1, whatever, so A will be greater than B. So here is 1, 0. Okay? You can do that as well. You can do that. So in that case here, so let's design this. So here is, let's call this S0, let's call this S1. So for S0, it will be equal to, you have only 1, 1, so it's A B bar. And S1, again, you have only 1 here. So this will be basically A bar B. And that's it. That's it. So let's try these cases. So if A and B are zeros, then S0 will be 0 basically, and S1 will be also 0. If A and B equal to each other, equal to 1, again S0 will be 0 because B bar will be 0. So we'll cancel everything. And S1 will be, A bar will be 0, so again 0. So look, when A and B are zeros or ones, I mean they are equal to each other, the outputs are all the time is 0, 0, which is really nice. Okay. Another case, let's take A equal to 1 and B equal to 0. So here A is greater than B. So I should see the output 1, 0. I mean, S0 should be 1 and S1 should be 0. So let's check that. So S0 equal to, it's equal to A B bar. A is 1 and B bar, remember B is 0, so B bar will be 1. 1.1 is basically 1. So S0 is equal to 1. And S1 will be A bar with A bar is 0 because A is 1 and B is 0, so 0, 0, it will be give you 0. So look, when A greater than B, you see this output 1, 0. which means really A greater than B. That's correct. Finally, if A is 0 now and B is 1, let's check. So S0 will be, A is 0 now, so 0, and B bar, B is 1, so B bar will be 0, so 0.0 will be 0. And the S1, let's check. A is 0, so A bar will be 1, and B is 1, so this will be 1.1 will be 1. So look, when you put A0 and B1, you got 0, 1, which means A less than B. Look, 0, 1 here, this case means A is less than B. Okay, you can do that as well. And it's your design. Someone may say, okay, no, I don't want the 0, 0 to be assigned to the case that A is equal to B. Can I make it 1 to 1, 1 and 1? Yes, yes, that's fine. Of course, this will change these, these equations. Okay, but what you really need here as a designer is to assign some case, some combination of these two bits, S0 and S1, and you will say that whenever I have this combination, that means A is greater than B, or A is less than B, or A is equal to B. That's it. Okay, it's your choice. So these combinations is the designer a choice. It's your choice. You can choose them in whatever you like. Okay, and that's basically will be your homework. So we will assign some cases for these three cases: E equal to B, A is less than B, A is equal to B. Then you do the Carnot map and get S0 and S1. Then make the VHDL code. It will be very nice. Okay. So you have here many options basically to do this design, the 1-bit binary comparator. You can go with this design here, in which you have three cases: A equal to B, A is less than B, A is greater than B, so 3 bits. Then you design each of them by its own, so you will have 3 equations. Okay, or you can go with this design here, in which, okay, we have 3 cases in the output, so we need 2 bits, because 2 bits basically can represent 4 different stuff. Okay, but you only need 3. That's even better. Okay, so then you say, for example, if I have A equal to B, I will have such combinations, such a combination like 0, 0 or 0, 1, 1, 0 or 1, 1, whatever you choose. Okay, and if I have 1, I will have this different combination. If I have 0, I will have, or I'm sorry, less than B, I will have this combination. So the basic condition is that you have 2 bits, and the 3 combinations that you choose must be different. Look, they are different. They must be different, of course, because these are 3 different cases. Okay, guys, that's it for this 2-bit binary comparator. I hope it was clear for you. Thank you very much for watching this video, and see you in the next video. Bye-bye.